Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My name is Amy Draves, and I'm here to welcome Mario Livio to the Microsoft Research Visiting Speaker Series. Mario is here today to discuss his book, Brilliant Blunders, From Darwin to Einstein, Colossal Mistakes by Great Scientists That Changed Our Understanding of Life and the Universe. Thankfully, science thrives on error since none of us has mastered perfection. Mistakes are inevitable and, in fact, are an essential part of pushing the envelope forward in any field. Mario Livio is an internationally known astrophysicist at the Space Telescope Science Institute. He is the author of several books, including The Golden Ratio, which won both the Pinot Prize and the International Pythagoras Prize as the best popular book on mathematics. Please join me in giving him a very warm welcome.
Thank you. It's my first time here, so it's really exciting, I must say. And I'm not surprised, by the way, that most people are watching online, this being Microsoft. So this is actually just to let you know, the book came out yesterday. So one day later, and I'm already here, coming all the way from the East Coast. So it's okay. So let's see what this is all about. So the book is about 5 giant scientists, all very big luminaries. And each one of them, I've chosen one major blunder that they have made. And there is a thread that goes through all of these 5, and that's the thread of evolution. Evolution of life, evolution of the Earth itself, evolution of stars, and evolution of the universe as a whole. So let me start. Now, in the presentation here, I've only chosen 3. And I may even cut it a little bit shorter because I want to finish in about half an hour and leave some room for questions and so on. So, but I have about 3 here. So let's start with what we know about life on Earth. And the first thing we notice about life on Earth is its diversity. I mean, wherever you look, there is something there. You know, you go out here, there are plants, there are birds, there are dogs, there are people, there are this. And plus, you take a teaspoon of dirt, there can be thousands of species inside that alone, and so on. Nobody actually even knows how many species there are on Earth. The latest estimate is at 8.7 million, but estimates range all the way from 5 million to 100 million species. So lots of species here of life on Earth. The second thing that we notice about life on Earth, which is remarkable, is adaptation and symbiosis. So adaptation, you know, it so happens that, you know, the body of the bee has the size that it exactly can get into the flower from which it feeds, but at the same time the pollen, you know, gets stuck to the body of the bee, and then it propagates the other plants and so on and so forth. So all of these things have led people to think that there must be some grand design behind all of this. And the example I gave here is this clownfish that lives among the poisonous tentacles of the sea anemone. And they live in perfect symbiosis in the sense that the fish protects the anemone protects the fish. The body of the fish is covered with this mucus, which protects it against the poison of its own host and all that. So all of this, you know, so over the years, people say, oh, there must be something really, really very designful behind all of this. And this lasted for centuries. And then came this one person here at his old age, Charles Darwin, and in one blow changed all of that. So this part is, of course, was about evolution of life. Now, when I research books, I tend to go to the places where the people that I'm discussing lived and so on. So in this case, I went to Cambridge, where all of Darwin's stuff is. I actually held in my hand the first copy of The Origin of Species, and so on, which is that, and so on. So he really changed the whole thing. And what he did is really remarkable, and it is probably the best non-mathematical theory ever formulated about something. Now, I put this here only because the design is so pretty, because actually this is not very accurate from a biological perspective. For example, it gives you the impression maybe that humans are more advanced than tigers or things in terms of evolution, when in fact that's not true. Evolution really behaves more like a bush than like a tree. It's not that there is something at the top. It's humans evolved in a certain direction, and elephants evolved in another direction, and so on and so forth. But it is true that those life species over there are more perhaps advanced than the bacteria that from which life originated, and so on. But it's a very nice design. In any case, the theory that Darwin developed, the theory of evolution, why is this not? Darwin almost never, he never actually published genealogy trees like this. He didn't publish a single one. However, in his own personal notes, he did sometimes draw them for himself to guide his thinking. And this one, which also I saw directly, you see, it's an interesting one because he has primates here and he has men right there at the top. So he drew this for himself, but he never published such things. Now, his theory was a theory that relied on 4 main pillars, and those 4 main pillars are supported by one mechanism. So I took this Hindu mythological drawing because it shows, 4 pillars on which everything rests, and all of that is standing on, supported by one mechanism. And I'm sure you know this. There is a story that people always tell about Bertrand Russell, which almost certainly never happened, but it is such a good story that you cannot not tell it, which is that, that he showed something like this, and then some lady asked him, and on what does that giant turtle stand on? He said, on another giant turtle. And on that giant turtle stands yet another giant. And on what that, he said, lady, I'm afraid from there it's turtles all the way down. So he probably never said that, but the phrase remained. So these are the 4 pillars: evolution, gradualism, common descent, and speciation. And what do I mean by every one of them? So first, there is the concept of evolution itself. Before Darwin, people were saying that species were immutable, that the way they are now, they always were. Species always existed, and so on. Darwin said, absolutely not. The species that are now actually did not exist. There were other species that existed and it became extinct, and from them came other species, and from them came other species, until we got what we got today. It's not that what is now was what always has been. Second is gradualism. He borrowed this from the geologists. Geologists basically said, we see changes in the earth, but they are extraordinarily slow. In fact, they are so slow that for all practical purposes, we actually don't see a beginning and don't see an end. It's things at the same rate that things are happening now, they happened before, and they happened before that, and they happened before that, and so on. So Darwin borrowed that and said, look, the changes in this evolution that you're going to see are extremely slow. They take hundreds of thousands of generations. So don't expect to see one species turning into another, and so on. Then there is common descent. Common descent is the idea that everything started from a few or even one life form, basically. So it's a bit like a tree where you have one trunk, then you have these branches, and then you have the twigs, and and so on, and this. So common descent, everything started from one thing. And finally, there is speciation. Namely, he had to address this question of how come that there are so many species today. And he said, well, the reason you have so many is because you have branching. So at every node, you basically double the number of species because you get more and more and more. And this is the only drawing that actually made it into on the origin of species, which is how you get this branching and nodes. And by the way, notice here he said at the top, I think. So he was a very modest person in terms of his. And all of this is supported by this one mechanism, which, what is that mechanism? That mechanism is natural selection, of course. So natural selection is, philosopher Daniel Dennett, who I think was in Seattle 2 days ago or something, if I'm not mistaken, because I'm speaking at town hall tonight, and I think I saw that he was at town hall 2 or 3 nights ago, said that natural selection, he thought, was the single best idea that anybody has ever had. And I kind of tend to agree with that, because it's an amazing idea. And the idea is, what Darwin said was, you have a certain characteristic. If a certain characteristic gives you a little bit of an advantage, and if that characteristic is also inheritable, then what happens is that over time, this characteristic will see more and more of it, and so on. So you first needed to give it an advantage, but also you had to be able to transfer it to the offspring, and so on. And here I just put in a few examples. I mean, this is a very nice example. There was this peppered moth in England that in the 19th century, there were lots of it, and it is light colored like this and so on. But then in 1848 started the Industrial Revolution, and they were burning lots of coal and stuff and so on. So all the trees and things became dark, and so this became the target of massive predation because it lost its camouflage ability, and they almost became extinct. And instead, the melanic, the dark species of that type of moth actually started thriving in those conditions. But then what happened is that they started to adopt somewhat cleaner practices, and as they adopted greener practices, the light-colored moth came back and did not become extinct. This shows a rat snake, and the way it, in different environments, it developed different colors, and so on and this. And of course, the best examples we see are with bacteria, where it now has become almost a disaster in that, there are bacteria now that are resistant to essentially all antibiotics. And there will be more and more of this, and we have not discovered new antibiotics for at least 15 years or so. So it's going to become a problem. And of course, the reason that we see this in bacteria is that, first of all, the population is enormous of bacteria. And second, that they multiply like crazy. And, every 20 minutes, they multiply and so on. So what happens is that you get the whole of evolution and natural selection compressed. And you get that. Now, so all of this is great, and Darwin did all of this in a fantastic way, but where is his blunder? So here is the blunder. Darwin didn't know any genetics, and that's not surprising because nobody knew genetics at the time. So we cannot blame him for that. So the theory of heredity that existed at the time was that characteristics get mixed like the mixing of paints. And Darwin, because there was nothing better, he believed that that is the case. You take what the mother gives, what the father gives, you mix them like you would mix paint. So the fact that he took that is not a mistake. That's all he knew. The mistake is that he didn't realize that if this were truly the theory of inheritance, then natural selection could never have worked. And I want to explain this a little bit, why it could never work like this. So let's look for a second. Imagine that you have a certain, I write this in terms of genes here, but of course there are no genes in blending heredity. But imagine that there is a quality that A is black, big A is black, and small a is white. And what happens in blending? You get one thing from this, one little a from that, you combine them, they blend like a color, they become gray, but they blend, so there is no really individual A and A, let's call it A1, the thing that you get. So basically what happened is that once you take two of these, you get something that already the color black has disappeared, actually. Even after just 1 or 2 generations, you don't see black anymore. Now, in Mendelian heredity says No, it's not like mixing of paints. It's more like mixing two decks of cards, where, if you have a jack, the jack retains its identity. No matter how much you shuffle the decks of the cards, the jack remains a jack. And you will always, if jack gives you an advantage, then you can find the jack sometime down the line, okay? So here is what would happen in Mendelian hereditance. This thing will come together and they will do a gray, but this gray will give one black and one white, and the same for that one. And when this combines, when this A will combine with that A, it will give black. And we combine like this, they'll give gray, and otherwise it will give white. So you still have the black in there. So, of course, this is a completely different thing, and Darwin somehow failed to understand this, that no matter how much, let's suppose that black gives you an advantage, well, guess what? In blending heredity, there is no black. After 2 generations, there is no black anymore. Now, once it was pointed out by an engineer named Fleming Jenkins, Darwin did get the idea that there is something wrong. And at some point, he actually wrote things that, show that he almost thought the correct way. For example, in 1857, even before the mistake was pointed out, he said that propagation by true fertilization will turn out to be some sort of mixing and not fusion. And then in 1866, he noted something that was seemingly so trivial, but only then it hit him, that every female in the world is producing distinct male and female offspring and not some mixture hermaphrodite. So it must be that there is something that is not quite, like mixing of paints. So he got that. Now, some people suggested that maybe he got that from actually reading Darwin's, I already explained what is here, from reading Darwin's paper. Now, basically what is explained here is that if I have a black cat and a population of 1,000 white cats, then in blending heredity, after a few generations, I'll just get barely a shade of gray, and that will be it. While if you do Mendelian heredity, the black never disappears, and if indeed it gives an advantage, it eventually could turn the entire population black. Now, no fewer than 4 books suggested that maybe Darwin read at one point Mendel's paper. So I decided to look into this, and before me somebody named Andrew Slater looked into that, and from the Darwin Project. And so basically, let me tell you what the story is. First of all, in Darwin's possession, he didn't have any copy of Mendel's paper. Mendel's paper was published in an obscure journal, and Darwin didn't have it. What is true is that there was a book in Darwin's possession in which Mendel's work has been mentioned. And this book was by this gentleman here, Wilhelm Olbers Focke, a German biologist. And I held that book in my hand and actually had a picture of that book taken. You know why? Because do you know where Mendel's work is mentioned in this book? It is in those uncut pages here, in the book that was in Darwin's possession. Darwin never read that book. Plus, had he even read that book, it would have taught him nothing, because this guy Focke himself did not understand the meaning of Mendel's work. So Darwin didn't know of Mendel's work. The next person I'm discussing here, not in the book. In the book I go to Lord Kelvin. Here I'm going to Linus Pauling. Linus Pauling, I'm going to be in Portland tomorrow, and he came from Portland. I actually gave a talk once in his house in Portland. Of course, he spent most of his career at Caltech, but he was originally from Portland. So Linus Pauling was perhaps the greatest chemist ever, certainly the greatest chemist of his generation. He's the only person ever to have gotten 2 Nobel Prizes by himself without sharing them with anybody. Well, one was for peace, but he didn't share that one either. So he got two Nobel Prizes without sharing. And Linus Pauling had first an incredibly successful model of proteins, and this is that model. This is Pauling when he was relatively young, and this is the same Pauling when he was older, still with the same model of proteins. Now, what did he actually do? Pauling turned around the whole thing of thinking about structure of molecules, and in particular proteins in this case, and so on. What other people were doing is they were doing X-ray diffraction experiments of the molecules. Namely, they were basically shining X-rays onto the molecule, seeing how the X-rays are scattered, and using Bragg's law to try to determine the structure of the molecule. Pauling decided to go the other way around. He said, I'm going to use structural chemistry. Namely, I'm going to use everything I know about chemistry, the sizes of the sub-molecules here and so on. I'm going to try to construct something and then test it against the X-ray diffraction images. So basically, in 1948, when he was sick at Oxford, he on a piece of paper, he started doing these models for certain proteins. And at first he decided that the carbon atom and the atoms that connect to it have to be in a single plane. And then he started folding this paper. You can actually see here the signs of the folds that he started to do. And eventually came up with a structure that was called the alpha helix, which is this structure for the main structure of many proteins. And this was an incredible structure, and it explained almost everything that was seen, except that it had 5.4 angstrom between the rungs here, while the X-ray diffraction things showed 5.1 angstrom. You might have thought, well, so what, you know, and so on. But he was very disturbed by this, and he actually sat on this model for almost 13 years. And testing every possible thing, you know. He asked Robert Corey, who was his assistant, to test the structure of the individual building blocks and everything, you know, and so on. And then after 13 years, he convinced himself that his model must be right, and maybe the 5.1 angstrom signature comes from something else. And he published it, and it turned out that he was correct. And this indeed came from just from the fact that there were two spirals, one wrapped around the other, and so on. So this was a huge success. But it was almost too big a success in the sense that it actually was bad for him when he went to try to discuss the structure of DNA. So already in 1948, long before the structure of DNA was discovered, he wrote the following. He said that if the structure, you see, in DNA you need to have something that manages to replicate itself. He said the best way to have something that replicates itself is if it's made of two parts that precisely complement one another. If it's made of two parts that complement one another, then if you have half of it, you can immediately do the other half, because they, you know, if this one has something sticking here, the other one has a hole, and so on, then, you know, if you have the hole, you know that there is something sticking, and so on. So this he wrote in 48. Then there were the Chargaff rules. There was this chemist, Erwin Chargaff, who discovered that, you see, DNA is made of phosphates, of sugars, and of bases. These are the bases, and they come of two kinds. They either have a single ring or they have two rings to them. And they have these names. I'll call them for short A, T, C, and G. Erwin Chargaff discovered that in any piece of DNA he could take, the number of A's is equal to the number of T's, the number of C's is equal to the number of G's. This also sort of hinted at something that a two-fold type structure. He knew this. Pauling knew this. And yet, he came up with a crazy model that had 3 strands in it, and
This is Linus Pauling's failed attempt to predict the structure of DNA. The problem with his triple helix model is that the phosphates form the helical core, with the bases pointing outwards. This would be impossible under normal cellular conditions. Each phosphate group is negatively charged, and so many negative charges forced together would repel each other, literally driving the structure apart.
so Pauling came with a model that was built literally inside out, had 3 strands instead of 2, and could not have been stable because the negative phosphates would have pushed the thing apart. And he tried to hold it together with hydrogen bonds, but if hydrogen was supposed to hold the structure together, then this thing would not have been an acid, because an acid is when you put it in water, it releases hydrogen. That's what an acid is. And this could not release hydrogen because hydrogen was kept to hold the structure. So it was something horrible. So one of the things I do in the book for every one of the scientists, I try to do a little bit of amateur psychology. Now, this is only amateur psychology because number 1, I'm not a psychologist. Number 2, because all these people are dead and I cannot really analyze them in any way. But I try to sort of get into their minds and see what led them to these things. So very quickly, first of all, do you know how long it took him to publish this model? 1 month. So why did he rush so much? How did he forget about his own statement about this complementarity and the Chargaff rules and so on? What about basic chemistry? This wasn't an acid. This was the world's greatest chemist. How could he have missed that? So very briefly, why did he rush? Not because of Watson and Crick. He hardly even knew them. He didn't know they were working on this. But he did fear that Bragg or some of the London people, actually, who he knew had better X-ray images than he had, could come up before him with the model. Forgetfulness, it's funny. But, one of the reasons may have been that he didn't like Chargaff very much. He met Chargaff. They were on a trip together to Europe on a boat. And Chargaff was this very intense individual who kept nagging. They ran into each other and he kept nagging him about his rules and things, and Pauling just couldn't run away faster, and so on. So he probably didn't want to remember much about this. What about chemistry? He almost certainly fell victim to his own success. Namely, what he learned from the proteins example was that his initial model was correct, and that once he has the basic model correct, even things he thinks are problems, at the end find a solution. So he thought that the same will work again here, he can work the magic again one more time, Yeah, it wasn't exactly an acid, it didn't exactly hold together, but the structure kind of looked nice and so on, and this, so maybe this. So that was that, and this is why it didn't work. Of course, the correct structure was found by Watson and Crick. The bases are really at the inside. A connects to T, C to G. This is why they are equal in number. They exactly have the complementarity that Pauling was talking about and all that. So, of course, once they did this, that same day when they found the correct model, they went to the Eagle Club. I took this picture at the Eagle Pub. There is this plaque there which says, this is where Francis Crick stood up and said, we discovered the secret of life. In the pub, he announced that. So, and I showed you how they looked when they were young, so just to show you also how they looked when they were old. Since then, of course, Crick has died. Jim Watson is still alive. So I think I'll stop here because it's a good place to stop. So I only did 2 of my people, but I think you get the flavor of what it is. I do have, a third person here, but, since you can get the book, you can read all about this. There are anyhow 3 more and so on. So I'll stop here and perhaps take questions. Thank you. Any questions? Yes.
How did you come with the idea for the book? What was pushing you?
Yeah, so why did I come up with the idea for this book? So there were a number of reasons, actually, and I can tell you what they were. So one was that I think it's comforting to all of us, especially who are in the sciences, to know that much greater scientists than us also made major blunders. So I think that's, it's a good feeling, even these giants. The other 2, by the way, So I talked here about two of them. There are Lord Kelvin, I said. There is Fred Hoyle, and there is Albert Einstein. Okay, so all of these are giants. The second reason is that I think that too much, more of the general public, I'm not talking about people who work in research, and so on, got this idea that science is a kind of a success story that goes from A to B in a straight line. And that nothing can be further from the truth. I mean, that's not how science progresses. Science really progresses in this zigzag path with lots of blind alleys and, lots of things and so on. And I wanted to give this sense. All these blunders, by the way, I call them brilliant blunders because, number one, they were made by brilliant people, but also in one way or another, these blunders actually led eventually to breakthroughs. So sometimes breakthroughs require blunders. There are things, I'm sure you know this, I mean, there are things that are inaccessible by incremental science. You kind of need to, think outside the mainstream to actually really get to a real breakthrough. And thinking outside the mainstream often encounters blunders. That's how it works. So that's the other reason that I wanted to do. So yeah, plus, these are people that I like at some level. And I also chose them, I said, because they were connected by this thread of evolution. Yeah.
Have you had any blunders yourself? And have you met any of these contemporary, at least the contemporary people that you write about?
Well, first of all, I made lots of blunders by myself. I don't know how that any of them has been a brilliant blunder. But also I don't pretend for a second to have worked on problems that are as fundamental as the people who who I describe in the book. So yes, I made a good number of blunders, and I also benefited from some blunders. I'll give you an example because I'm an astrophysicist. I'm a theoretical astrophysicist. So I don't do observations myself. But when I was just towards the end of my PhD, there was a French astronomer who will remain unknown, who looked at, there are these things called planetary nebulae. These are things that happen late in the life of stars like the sun, when the star ejects its outer layers and the hot core illuminates everything and creates these beautiful shapes. Until then, everybody thought that the central stars of planetary nebulae are single stars. It's just the core of one star. That person published 6 planetary nebulae. I don't mind saying it was a she, that she observed, and she claimed that they were all close binary nuclei, that there were 2 stars in the middle. And before that, nobody really claimed that. Now, as it turns out, with the years that have passed, none of those 6 objects that she pointed out to turned out to be a close binary nucleus. Not one. However, because of her work, lots of astronomers started looking more carefully in this, and lots of close binary nuclei were discovered. And I actually did quite a bit of theoretical work of how you form the shapes of planetary nebulae with binary nuclei, and so on. So I benefited from a blunder, but the whole of astronomy benefited from that blunder. Was there something else you asked?
Have you met any of these?
Have I met? No, I spoke on the phone with Jim Watson. I have met Fred Hoyle once, but I didn't know him. I spoke with his son at some length, and I spoke with people who worked with him and postdocs, and so on in this. Einstein is one of them. I clearly have not met Einstein, but my Einstein number, compared to the Erdos number who wrote a paper with him, is 2, which is the smallest you can have today, because I wrote a paper with Nathan Rosen from the Einstein-Podolsky-Rosen paper. So that's about as close as you can get to Einstein.
Einstein left when I came in.
So yes. So no, I've not met them, but yes. Darwin, of course, I could not have met. Yes.
I have a question from online. He's saying lots of these blunders occurred many years ago. Any recent blunders last quarter century that you would consider brilliant?
I don't know about brilliant, but there have been certainly blunders and serious blunders, even in recent years, that at some level have opened areas. And I can mention some. For example, the very first announcement of planets around the pulsar turned out to be wrong. These were the very first extrasolar planets discovered in 1991. They turned out to be wrong. But in the same year, somebody else discovered planets around the pulsar that were real. And that is, now a known class of objects. Many of you, I'm sure, have heard very recently, actually just a couple of years ago, of this announcement of arsenic-based life. That there were these bacteria that have in their DNA arsenic instead of phosphorus. This turned out to be wrong. But, the announcement of that and all the research work that went around proving that this was wrong actually opened some interesting avenue, and it got people thinking about, really, could you have maybe, arsenic is somewhat similar to phosphorus in its properties, and so on. So these were not brilliant blunders in the sense of the blunders in the book, but because they were in very interesting areas, they did stimulate, other interesting research. Yes?
The Newton blunder.
So Newton, okay, I decided, by the way, consciously decided not to go as far back as that. I specifically went only far, because you see, if you go far enough back, then clearly even the greatest geniuses, it's Aristotle, almost everything he said in physics is wrong, yes? And yet he was a genius, yes? But it's just because he worked at a completely different time. So I decided not to go too far back. Now, I did look into Newton. I knew I don't want to do him, but I still look at it. And Newton was one of these annoying people who almost makes no mistakes. Of course, he did one crazy thing he actually dealt a lot in alchemy. So that entire branch of his work was crazy. But in the more serious work he did in physics, you can look a lot and you will not find any mistake. Einstein, by the way, did many mistakes. I chose one blunder to concentrate on, but he did many mistakes. Pauling, some of you may know that late in life he became obsessed with vitamin C and all that and so on. Fred Hoyle was one of my people. I talk about steady state, but he had things about life that were very wrong and so on. So most people make more than one serious blunder and so on. Newton was very annoying in that respect. Any other questions? Yes.
I have an obscure question, but I'll try and frame it right. On your blog, you referenced 4 elements.
One of my recent blogs.
One of your recent blog posts.
Yeah.
That reminded me of a book called Science in Babylon from some Yale lectures, and in there's an argument that Western science, because it came from 4 elements, and 4 was significant, whereas 5 elemental history in the East kind of sent them off in a different way. Because you kind of jump around from so many different fields, like Pythagorean theorem, golden ratio, is that anything that you've spent time thinking about in terms of this validity of 4 versus 5 elements?
No, not a lot of time. However, I will say that, and I think I mentioned this in the blog, that even when the ancient Greeks, talked about 4 elements, they actually did add a 5th. The quintessence, which was the 5th element, which Plato and Aristotle actually talk about, which was supposed to kind of more represent the universe as a whole. So they also talked about 5 in some way. There were the 4 basic elements that formed everything kind of we see, but then there was this 5th element, which was, for Aristotle, it was the ether, and so on. So, yeah.
I know that he's not at the same scale, but what sort of blunders do you think are going to come from Wolfram's new science, like mathematical, or that sort of...
Did you mention Wolfram, you said?
Yes.
Yeah.
I don't know.
So, so I imagine what you refer to is this idea that everything is some sort of cellular automata and you should do all of in those terms. I think that this is a very interesting thing. I mean, basically what he would say, look, instead of going along the path that took us from geometry and number theory through differential equations and whatnot, we could have gone through a path that would start with some very simple rules, like, you know, you have some pebbles, if you put a white pebble, put a black pebble next to it, and I don't know what, basically small computer programs, you will call them today. And you could develop a whole mathematics based on that. And I think that's a very interesting idea. I do know, now there are people, and I imagine there are people here who work with cellular automata and so on. I don't know any scientist that as a result of Wolfram's thing, you know, sort of stopped solving differential equations and started doing cellular automata. But you can argue that this could have happened, and you know, if there is life somewhere else, maybe they would have gone that path. I mean, I believe that we have gone the path of geometry and number theory because of our particular perception system. Namely, we are extremely good at seeing what is a straight line and what is not a straight line, for example. Or we're very good at seeing edges of things. So this really helped us, you know, develop number theory and geometry. But if there is some other species that, I don't know, sees mostly in the infrared, or I don't know what, you know, maybe they would come up with something that's different. So it's certainly not a blunder. I mean, it's a different path, and I think it's interesting. Yeah.
There's a lot of questions going on online, so I'm just going to ask you one of them, which is, they're saying, as an astrophysicist, what do you think about Pluto?
What do I think about Pluto? This I expect to hear at a talk in the kindergarten, not at Microsoft. They are very emotionally attached to Pluto. I think the entire discussion is absolute nonsense, to be honest, because Pluto has not changed what it was. It remained the same thing. It is just that at one time, we didn't know about the Kuiper belt. We didn't know that Pluto was just one object out of thousands and thousands that are in this Kuiper belt that is around our solar system. And it just is closer, and it's one of the biggest. It's not perhaps the biggest, but it is one of the biggest. So it was discovered and you know, classified as a planet. Since then, we know of this Kuiper belt. We know that there are all these billions of objects in it, and we know of at least one that is bigger than Pluto, probably, although they are pretty close, you know, and so on. So then the question came about, well, wait a second, so what should we do? What, we'll call all these millions of objects planets? Or shall we just recognize the fact that Pluto is one of this Kuiper belt, and it was demoted from being a planet to be called a dwarf planet, okay? But it hasn't changed what Pluto is, you know, and so on. So should we have changed the name or not? Well, it depends on taste, I guess. If you think, well, for historical reasons, it was always called a planet, let's continue to call it a planet, who cares? Or you say, well, I want really to be more accurate from a physics perspective and blah, and I demote it from being called a planet because I define planet by a certain number of criteria and it doesn't meet all of this. That's all there is to it, you know. To feel so emotionally attached to this business is a bit strange to me. It's somehow the planet that all Americans love the most for some reason.
Well, thank you so much. There are more $10 books if anyone's interested.
And I'll be happy to sign all of them. So.